Thank you very much.
Thank you.
My name is Adrian Will. I'm from Argentina. I am the director of GTIA, a small research group from Tucumán, Argentina. I will be presenting an equitative, autonomous, distributed demand-side management system for peak shaving and the air conditioning trap problem. That's a very real problem for us. So what is the problem we are trying to solve? We are trying to solve two problems. The first one are weather-related energy prices. It is happening a lot, and it's happening over and over again in harsher conditions. You have extreme weathers that exceeds expectations and previsions, and you get weather-related energy crisis. In the two cases I'm going to refer today are very briefly, winter case of Texas in February this year, and a case that happened in my city some years ago. They both were weather-related and provoked serious economic losses, and in the case of Texas, loss of lives. Over 100 people, up to 600, depending on the reports. So what happened in Texas? Freezing temperature caused wind generator to go offline, and according to other sources, the very freezing temperatures caused gas pipelines to diminish pressure, and many gas-powered power plants to go offline. So the production capability of the state of Texas went 30 gigawatts below the original plan installed capacity. What happened in Tucumán is the inverse case, but it's very similar. The production capacity was untouched, but the consumption of energy went over the top because of several days of really high heat wave. So it exceeded all expectations of consumption, and it provoked serious damages. The second problem is, even if your grid stands the consumption, there is a really close to the limit consumption on hot summer days and hot and very cold winter days that exceeds your spinning reserve. So you need to use thermal centrals. That is the usual way to solve it. But at least here and in many other places, they use open cycle generators that use gas or fuel, and you have a serious problem of greenhouse gas emissions. But it's limited to the hot spots, to the hot summer days. So if you take down this excessive consumption on hot summer days, you will get a really lower greenhouse gas emissions. And once again, many people here in buildings or neighborhoods is trying to, mainly for a reason of cost, trying to get to renewable energy, but you need to respect a maximum level of energy of consumption, otherwise your system will go bankrupt, and that is a problem. So we are trying to respect a maximum level of consumption. And these are the data for Texas. As you can see, the red line was the historical maximum. That was 66 gigawatts. The reference is there. On a given day, the consumption exceeded the historical reference, and it was expected, the light blue line, to go really over that. But the problem was this portion of consumption here. So the peak shaving alludes to the fact that you don't have to really lower too much the consumption in order to solve your problem. You need to shave something off the top only. If you get your consumption to below the dotted line, you will have half the problem or even less. In the case of Texas, it was only 10 to 12, 14%. It was that you need to take down the whole consumption of the country. And that is something that it can be done. That's the case of Argentina. We are in Tucumán in 700 megawatts for the record in hot days. That's an estimated 300 megawatts due to air conditioner. That's almost half. What I'm showing in the picture, in the shaded portion, is the estimated consumption in the neighborhood due to air conditioners. That is exactly half in the hotter part of the day. So half of the consumption is due to air conditioners, and it provokes serious problems. Burned in 2013, it was protections jumped. There were several damages to lines, medium tension lines, substation transformers, and such. You don't get people today because you can use water and you have other ways to cool off. In the case of freezing, you freeze to death, but there were no casualties because of use of water and other techniques. But it was a serious crisis, and we are sure it will happen again eventually. So we needed to do something about it. So the problem is that once the consumption goes up near the top, you start load shedding in order to stop the crisis to go further. And the crisis in Texas got really serious. According to some reports, it was 5 minutes away to a complete blackout. So you start taking down substations according to the most charts, and you completely cut the power to people. That's not a nice thing to do if you can avoid it. So the idea is to control only fridges and air conditioners that are the main part of the problem. So the idea is to diminish 10 to 15% of the total consumption in weather-related energy crisis by controlling heating and cooling devices, and minimize or avoid completely load shedding, avoid cutting power to people. That's always achieved by keeping the total load below a predefined maximum. How is it done today? There are many systems doing this, but you use Catalytic system. That means you have a centralized control that asks each node different message and gets an answer. So it's incredibly complex and impossible to do city or statewide. And you have other ways to do that, talking to your neighbors, using transversal communication. That's a flock of drones. But you can do it in a flock of drones where you have real-time, easy communications, not going through walls, and in an urban setting with RF completely jammed and such. So you only can do a broadcast. You broadcast one message, in this case the consumption in the transformer, and you make do with that. So smart demand side energy management system alludes to the fact that work on the customer side. And controlling, you need to install a device, but think of a small device like a microchip or an Arduino, controlling air conditioner, heaters, freezers, and other heating and cooling related technology that, in this case, for this problem, are the main part of the problem. And the idea is to use short, coordinated 3 to 5 minute stop in order to lower the total consumption without disrupting customer comfort. One of the premises was to be as undisruptive as possible, and to do it without too much communication infrastructure or programming complexity. If you make a statewide SCADA, it will work, but it will be prohibitively expensive for most cities around the world. So the idea is to do it cheap. So as design principles, we wanted to minimize interference with the customer, no external communication, so broadcast only, to preserve customer privacy. I don't need to know if you have air conditioners, how many do you have, or if they are on or not. You install the device and it starts working, and that's it. It should be small and work in Arduinos or microchips, and could be explainable, no black boxes. There are a strong tendency today to not use black boxes, to not use parts that an engineer won't understand. So you install a sensor in your transformer, your building entrance line, or your energy source node, your energy supply node, where you get your energy and want to respect your maximum consumption. And you make a broadcast unit that broadcasts your information about consumption every second, every 5 seconds, every 200 milliseconds if you're lucky. Use a communication infrastructure strictly top-down. That means from the source node down to the devices. And every device must have its control unit, gets that information, and makes its decision. The decision of each device is based on an artificial immune system. These are the original equation of an artificial immune system posed by Gerner and Watanabe in 1995. But it's a too slow system for the application. And an air conditioner, traditional air conditioning, has a step-like function in the process of starting and stopping. So it's very, has the function you have to control has very strong variations. So this derivative and sum of concentration is a differential equation with slow reactions, and it doesn't work for the problem. So we adapted it, took out the derivative, and simplified it using only 2 terms. This is a squash function, a type of sigma function of this sort. This is 1/1 plus exponential of the difference in the energy you are consuming and the limit. That's the first term. Minus a kill, that's only 13 to 1/2. And the second one is 1/1 plus exponential of the consumption on your particular device minus total energy, the available energy. So why does it work? Because if your energy consumption is below your limit, this difference is below 0, it's negative. So you get on this side of the equation, and the probability, this is seen as a probability of starting or keep working, is close to 1 or high. Once you reach the limit, the probability get to 1/2, and after you go over the limit, the probability drops to 0. Then the same for the device. We had the problem that some air conditioners were big in size, and there wasn't enough energy to get them to work. So if there is enough energy, your probability to start is close to 1. And once you reach the limit, the probability drops to 0. But the shape of the function gives you margins close to the limit. It's very steep, so you get a smooth behavior, and it works just fine. Yeah. There are some thresholds to hold, but clearly, one important aspect is that it is clearly deterministic. It is clearly a program. It's not a black box, and you can adjust coefficients and predict what it's going to do in any particular situation. So it's an intelligence and not an heuristic. That is critical because it's explainable. And those are the simulation results. That's from 2 years ago. You have 100 air conditioners consuming at the same time 1 kilowatt each. And you set your limit to 75%, so 25% less than the limit, that's 75 kilowatts. And this is the total consumption. As you see, it's very, very quite well respected. These are the Gantt diagram of the 100 air conditioner consuming over time. Those are the small 3 to 5 minute stops. No one in any particular stop goes beyond the 3 to 5 minute limit. If you zoom up, if you add up that over an hour, you get this histogram, and it has the problem that it's unfair. You have air conditioners stopping without stopping, and you have 1, 2, 3, 4 that have stopped over almost half an hour. And we had to solve that. So we tried to implement that, and we faced 4 main issues. 1 non-technical, 3 technical. The first one was how to install or convince the people to install them. Well, first of all, you do not need to install it across the country or across the city in order to solve the problem. If you install it in 30% of the consumers, then you will have an impact. Yeah. You don't need the system working in every building all the time in order to solve the problem. Any partial installation will help. And in that sense, you should start with building those neighborhoods. One very important aspect is that if you have a close neighborhood or a big building, buying the energy by bulk and being able to respect the maximum makes the energy really cheaper. So that's our approach today. And technically, you have 3 points to solve that we have solved up to today. Too strong an influence of broadcast time. The message has to be really on time. If you start getting slower or losing packages, you will have a problem. An unfair distribution of stops that we solve also. And it's necessary to detect automatically the phase of the consumer and the device transformer relationship. You need to know the topology of the low voltage network. I will get into that. So what's the influence of the broadcast time? Your system is sensitive to delays in broadcast time. The first picture here is the usual 1 second, and you can see the limit is respected. You have small peaks over the line, but they are very small. You can make a relative error, and you see that's below 2% or so. And it's the price you pay for distributed control and no centralized control. So it's only little pieces that go over. As your message starts getting lower, you get a self-feeding effect, and it can get over the top even more. And if your delays get to 20 seconds or more, the speed can get ugly. You get bands going up and down, almost in a chaotic behavior. So this situation should never go to happen, and we're working on a safe mode in order to revert the system to a safe mode whenever you have a serious communication problem. But since it's a small message, smaller than an SMS, there are 5 numbers that you need to get to the air conditioner every 5 seconds, 10 seconds, and the system recovers okay. It's a realistic assumption that the system gets the log packages in time. And it's very cheap to do since you only have to do a broadcast. And this year advances, we got to make a fair distribution of the times. Some of these devices can consume more than ours, so it's not a fair distribution of energy. It's a fair distribution of stopping times. If I have a small 1 kilowatt air conditioner, I will have a 5 minutes or so stops in an hour, and my neighbor with a very large 3 to 5 kilowatt air conditioner will have the same 5 minute stops. I'm giving 15 minutes, and it's very fair. And we were able to do it without increasing the communication needs. If anyone wants to know how, coffee is on me, but I don't have the time to explain it in more detail. The last part was it was necessary to determine automatically the low voltage grid topology. Why? Because each air needs to know from which transformer is receiving the energy. It's logical because the decision is associated with the consumption in the transformer. So you need to know this air conditioner or this heater from which transformer and from which phase is receiving energy. And that must be done fully automated. If you want to do it, a citywide system needs to, you don't have to, it's impossible to make that update from human intervention. It has to be fully automated. You don't get to clean your data before processing it. You don't get to clean your results after. And it must work on small Raspberry Pi type computers. and it must have high precision. We are achieving 99% precision on the field. This was published last year. We have two publications on this subject. These are the most advanced system, and we're still working on integrating the phase identification system with this system I'm talking about today. You need to measure your transformer with a standard smart meter every 15 minutes. We are using average consumption every 15 minutes, but you can use other variables. It must be synchronized with the measures in the smart meters. That's standard. You can have a proportion of the smart meters measured from 10% up. So the assumption that you have all the measures was not realistic either. And you get the phase as a result. You get the phase to which each house is connected, or a zero if your house is measured, but in fact not connected to the transformer. So these are the simulations. The one in the left is a small 160 kVA transformer. You get your results within a week. A standard case in Argentina and worldwide is 250 to 300 customers for a 315 kVA substation transformer, and you need more data. You need 15 to 20 days in the standard case to get 90 to 95% precision in your results. And this is our most competitive part of the system. The picture in the right is 20% missing data in 100 customers, 10 days. And it's really impressive that it works. We have tested it up to 30%. And that corresponds to the yellow line, the orange line in the middle, that shows that you get your results to 90% precision with 15 days to 16 days worth of data. It's not magic, it's just good science, because working with the original Pearson correlation coefficient gives ugly result, but working with the first difference between the next measure and the first really separates the measurement and gets this result. So you have a wide difference between the correct phase in derivative and the two incorrect phases in derivative, and that wide difference is what makes it resilient, resistant to missing data. Anyway, you fill out these gaps, you will get the correct result because the difference is too wide. So it's very it solves the problem quite well, even in the presence of missing data. So what are the conclusions? It's a fully distributed smart demand site management system. We work on the customer side and mounting a communications network, but only top down. The only thing that the distribution company must decide is the limit that they set in each level. That's a number, and the system does the rest. It's capable of large-scale applications because you can pile up these systems if necessary. And it's low cost because, as I said, the communication infrastructure is only top-down, and the processing is minimal. As you saw, it's a couple of SAM, a couple of products, and 2 exponentials, so it can be programmed smartly and works in an Arduino. We have already done it in real tests. It preserves customer privacy because that's the main issue, because many systems like this exist around the world, but they have to be centrally controlled from the distribution. So the distribution company knows not only if you have the air conditioner, but they turn it off. So in this case, I don't need to know if you have it or not. I don't need to know if it's on or not. The system decides for itself on the air conditioner. It's fully explainable, no black boxes. It's a couple of equations with particular coefficients that respond in a predefined way, and you can ask questions and you can program the answers. But no black boxes. That is a huge problem nowadays. And you can get to 10-15% decrease in maximum consumption is feasible. It's doable, at least in Tucumán, because of the very large portion of air conditioning consumption. And it's minimal user discomfort, both in the way that we don't make long stops, and you get to do less power outages. You don't get to do rotational load shedding, at least in the substation transformer where you're controlling enough clients. So the idea is to do as little rotational load shedding as possible. Well, these are the references in case anyone wants to get deeper into the subject. Thank you very much.